So what is the correspondence problem? Well, basically, the epipolar constraint constrains what our solution is, but it doesn't solve our solution. So here we have a bunch of points in the left image, and we know they lie along the epipolar line in the right image, but the question is, what are the matches? And here in hypothesis 1, 2, and 3, coded in gray here, you can see these are different possible matches. And so for each point in the left image, we have to decide what the match is in the right image, or vice versa. So to help solve the correspondence problem, what we need are some additional constraints. The epipolar constraint was a hard constraint. That is, it must be true. It's enforced by the relative camera geometry. But there are other types of constraints which we might call soft constraints. One is similarity, which says that pixels in the left image should look about like the pixels in the right image if you have the right match. Uniqueness says that there's up to no more than one match of a left pixel in the right image. Ordering says if pixels go ABC in the left image, they go ABC in the right. And disparity gradient is limited. That means that the depth doesn't change too quickly. We'll talk about some of these today, but what we're going to start with is similarity. Similarity is essentially saying that the image patch from the left should match the image patch from the right. So to find matches in the image pair, we're going to assume, first of all, that most points that are visible in one view are also going to be visible in the other, so we'll go looking for them, and that the image regions for the matches are similar in appearance. So here's how we're going to do the dense correspondence. And dense correspondence meaning we're finding a match everywhere. For every pixel, let's say in the left image, and we're going to take a little window around that pixel, we're going to compare it with every pixel/window in the right image. And we're going to just pick the position that is either the most similar or the least dissimilar. And that best match, that's what we're going to assume is our corresponding point. So here's a very simple illustration. So I have a scan line across both images, and we're assuming parallel scan lines for now. And I've got my window in my left image, and I'm going to compare it to a bunch of windows in my right image. And the matching cost is computed everywhere. And so this is just a notional description of what the matching cost is a function of disparity, so how far off I am from the first match. And of course, the idea is, well, we're going to pick the value that has the best score. So I might use something called sum of square differences, which is the sum of the square differences. Wasn't that a surprise? No. What you do is you take the two pixel windows, you overlap them, you subtract them, you square the differences, and then you sum them up. So that would be a measure, and that's why at the top it says dissimilarities. Now, sometimes, let's suppose one image was a little bit brighter than the other image. You know, for some reason the gains weren't set so well on the camera. If I just do direct subtraction, even if the match is exactly the right place, because of that scaling of the intensity, I'm going to get square difference error, and it might not lead me to get to the best match. Now, we've already talked about how to eliminate the problem of scaling. Remember, we talked about doing normalized correlation, where we scale the value of the window so it has the same standard deviation. So you could do that here too. You could take your window and slide it across doing normalized correlation instead of sum of square differences, and that's actually a similarity constraint.